So, before we have any real quantum computing, we need to create enough qubits in the register. And at the moment, let's say that we have about 100 qubits as sort of the maximum that we've managed to put in 2019, 2020, beginning of 2020. So, how many years is it going to take before we can expect to see some real quantum computing? And assuming we start at 100 qubits, which is right now, and we need about 100 million qubits before we can do something really, exciting, like hack the internet, right? The RSA protocols. So to get to 100 to 100 million, we can make some assumptions. So if we assume that the number of qubits in the register is going to double every year, it'll take about 18 years to get there. If we assume that it's going to quadruple every year, then it'll take about 8 or 9 years to get there. And if we assume it's like exponential, if the increase is going to be exponential, then we'll get there in about like 10 years or so, 10, 11 years. So on average, I think it would be fair to say, given that up to this point, to get from 1 to 100, again, it's early on to really say for sure, but it looks like we're on the exponential curve. And so I think it's fair to say that we're going to be seeing some pretty interesting quantum computing done about 10 to 20 years from now. But before then, I expect that there are going to be some pretty interesting experiments done. So if you have half of that in your register, there's probably some other interesting computations that we can do that we haven't thought of yet, but we'll come up with in the next few years. So the interesting thing to know about quantum computing is that unlike regular computing, in regular computing, if you double your resources, you double your computation. But in quantum computing, in order to double your computation, you just need to add one qubit. So you add one and you've doubled your so-called computational power. But the reverse of that is that you need a lot more resources in order to make it fault tolerant, depending on fidelity and decoherence and things like that. So it's going to be an interesting journey. I think not everything has been fully understood at this point, which means it's a really exciting field to be in. So I'm looking forward to it. And again, it could be that the sort of computational problems that we explore are such that it really would be the case that doubling the number of qubits sort of doubles the size of our problem. As opposed to going exponentially with problem. I mean, just in terms of, for example, if we want to simulate molecules, maybe doubling the number of qubits would allow us to double the number of molecules that we can simulate, instead of being an exponential increase in the number of molecules we can simulate. So these are sort of the areas that I'm sort of poking into right now and exploring. The hardware seems like it's coming along at a good enough click, and in terms of the algorithms and the software space, it's hard to see anything truly inspiring, because it's hard to be inspired to create algorithms for a device that's going to exist in 5 years. And so I think once it's on the table and people are able to access it and play around with it, that's when we're really going to, I think, we're really going to have a lot of creativity, and I'm really curious to see the sort of things that we're able to come up with back then, or we're going to be able to come up with in the future. About 10 to 20 years, and hopefully something interesting within the next 5. So that seems to be how things are going right now.